committee, and I'm very excited to welcome you to our keynote and tutorials for 2022. So this is our second year implementing this type of event, and the first time we will have them in person. So what are the keynote and tutorials? Well, the idea is, in addition to the wonderful science you typically get at a great keynote, you also get to have a look under the hood afterwards in a tutorial that directly covers the material that the speakers are going to tell us about today. And so the speakers and tutorial leads have made all of their methods open and will walk you through a step-by-step tutorial so that you can promote open science, enable new analyses, and just get a better idea of what's going on behind the scenes. And so in addition to helping you implement their code, the tutorial actually gives you really great access to the types of scientific assumptions and interpretations that the authors make in their work. We really try to seek community engagement in this process, so we have an open submission process. Anyone can apply. And we selected these out of several outstanding proposals to try and cover the full breadth of different CCN topics, and obviously for their high quality submissions. So we're gonna, just one logistical note, we're gonna have both keynote presentations back to back right now, and then we'll have a 30-minute break where we will split the room in half, and then we'll come back for the two tutorials that will be held in parallel. All right, so our first keynote is going to be given by Mommenejad, and the tutorial will be led by Arthur Giuliani. So Ida is a principal researcher in reinforcement learning at Microsoft Research in New York. Her research focuses on the complementary goals of first understanding how humans build models of the world and use them for memory, exploration, and planning. And two, building and testing algorithms that are neurally plausible to also learn the structure of their environment. To do this, she uses a multidisciplinary approach that's really at the heart of the CCN community, combining reinforcement learning, neural networks, machine learnings, with experimental methods, behavior, electrophysiology, and fMRI. In addition to her many research contributions, many of you also probably know Ida as the creator and one of the co-hosts of The Learning Salon, which is an innovative weekly forum that brings together researchers in AI and natural intelligence, and it's been a really important contribution to our community, especially during the pandemic, and I think has really helped shape scientific discussions over the last couple of years. So we all have Ida to thank for that as well. And so today she's going to talk to us about varieties of human-like AI.
Voice on? Oh, yeah, perfect. Thank you, Elizabeth. All right. So let's go full screen. So hi, everyone. Thank you for showing up so early in the morning. I know that for some of us who are on the East Coast time, it might be easier than others. I really appreciate your presence here. I'm excited to tell you a little bit about, first, some varieties of human-like AI, different approaches to it, and what are the success and failure modes. And in the second part, I'll tell you a little bit about different reinforcement learning models and how, for instance, they can be tested on varieties of behavior. I will also propose that we could have generative adversarial post-publication review at CCN, and I will highlight with one slide, one example of why that would be important and how that's related. In the tutorial session, Arthur and I are going to discuss NeuroNav, which is a tool where all of you can test out different algorithms and potentially and hopefully, and that's what we are hoping you're going to do, code your own experiments using that tool and see how easy it is and give us feedback. All right, let's start with this. Before I go any further, I want to thank postdocs and grad students who have worked with me over the past 2 years that I've been at Microsoft Research during the pandemic. This is not an exhaustive list, but I just want to thank them, and if you see them somewhere, say hi and ask them how they're doing. Okay. What makes AI human-like? Some folks seem to believe that what's sufficient is passing some benchmarks. However, if the agent is solving human tasks above the baseline of human performance, we can't call no longer that human-like. If something is superhuman, it's not human-like. It's not helpful in capturing the accuracies and errors of human behavior. So another thing is some people say, all right, but what if we have something that performs on some tasks like humans? The fact is that most things do not necessarily transfer to other tasks. So they can solve some tasks extremely impressively and can generate a lot of hype around it, but they cannot solve many other tasks that seem to be very basic for humans. And some people believe this is just a matter of enlarging the size of the different kinds of algorithms and the number of parameters these algorithms have. But that has also planetary costs. Why don't we just take a cognitive science-based theoretical approach as opposed to just increasing the size of our parameters until we randomly stumble upon something that's more human-like? Another thing is that some approaches could be partially neurally plausible. However, if you look at the behavior they produce, for instance, on adversarial examples, they don't show human-like behavior. And I don't mean by that just the work that has been, the beautiful work on adversarial images, which, for instance, this cannot be identified by the original paper that was shown in 2015, or adversarial patches that just put it next to a banana and it turns into a toaster somehow. These kinds of things obviously were the earlier cases of adversarial images and patches. But later on, we also know that it's not enough for us to train these CCNs to just be robust to anything. It's extremely important for it to also make human-like errors on images that are adversarial to humans. And outside of one study, I don't know enough studies that are actually doing that. So if we look at behavior, in spite of some validity of convolutional neural networks, it doesn't seem to actually show human-like behavior, therefore perhaps something is missing there. Another example is chess. We all know that since late 90s, AI chess has achieved superhuman status. However, studies by CCN and some of my other colleagues at Microsoft Research, which continues, shows that if you show these sequences to grandmasters, they do not recognize the sequences produced by the superhuman AI as human-like play. And in another study recently that they haven't published yet, they also showed that if you train humans using these non-human-like sequences of superhuman chess players that are AI, they actually don't improve unless they are very naive about chess, where any kind of feedback is going to make them improve. So not only are these superhuman chess sequences not human-like, it also doesn't help people to get better at chess. So it's not that they're producing superior sequences we could learn from necessarily. So in a paper that will shortly come out in Philosophical Transactions of the Royal Society, I have proposed a rubric for human-like agents and neuro-AI. It's extremely simple, and by the way, please feel free to take photos of any slides. I know that it's too early for anybody to take notes. It's a very simple rubric, and it might almost sound completely evident, but I think it helps a lot to dissociate the contributions and not confuse certain successes for other kinds of successes. Some of these approaches might have the goal of being neurally plausible. Now, for instance, CCNs were making such claims. That doesn't mean they necessarily have a high score on the human-like behavior front, or rodent-like behavior if rodent is your favorite creature. And also, if something was very successful at benchmark passing and engineering, for instance, the superhuman AI chess, it doesn't necessarily mean that it shows human-like behavior or has a neurally plausible approach or representation to do it. I know it sounds very simple, but I think by decomposing these different principles along which there could be progress made and goals could be organized, we can see which of the approaches actually have multiple goals, so fall somewhere between them, and which of them might fall on one of the axes or two of them but not the other, and which of the approaches might be a little reaching their actual valid claims by suggesting that success in one area is necessarily translatable to another area. And I want to thank Ross Poldrak that yesterday he asked me a question, and I think in the conversation it came out that on some abstract level, yes, CNNs are neurally plausible or even do show some human-like behavior. And that's why this rubric is non-binary. It's not just 0 and 1 on these axes. You can say, okay, it's a 5 on the neural axis, and it's in a neural plausibility, or it's a 2 on the neural plausibility and a 1 on the behavioral plausibility. So it's easier to kind of place different studies' contributions without either diminishing them or over-exaggerating their contributions. Now, the library that we are going to talk to you about a little later is very inspired by the fact that I look at many different studies within any given field, and each of them is looking at a couple of tasks, and they say, oh, look at my model, it performs great on these tasks. But the kinds of tasks do not necessarily generalize to other tasks in the field. At some point as a field, it would be helpful for us to have a number of tasks on which any new model that wants to claim, for instance, that it's hippocampally plausible or that it's a model of navigation, it would need to be able to solve a battery of tasks in a human-like or rodent-like fashion, either behavior or its neural representations, not just 1 or 2 or a hand-picked versions. So one of our goals here is, instead of this roomy from 13th century way of everybody sort of touching different parts of an elephant, if we could merge these divergent visions into one by having a candle in our palm. And we're hoping that this kind of NeuroNav library that we're going to talk to you about is some version of that candle, and offers some approach that we can have to having easily composable series or batteries of standards for comparison of models. So we don't fall into some fallacies that I call the Russian election fallacy, and I'll show you a slide about it later, which is that one model all of a sudden performs radically better than others. It could be that you're not selecting the right tasks, or it could be that you're not doing justice to the other models you're comparing with. All right, so I hope that you join us for the next tutorial. And we are hoping that while currently it's just a library, it's going to at some point help us to create a benchmark with agents, tasks, and environments from neuroscience research towards neuroscience artificial learning. And for that, I have to thank Arthur Giuliani, who has been extremely amazing at creating this. And if you look at the code is written beautifully, as well as my grad student interns, Brandon Davis and Sam Barnett last summer, who helped out. This is what you will see, just in case you want to check it out. There is the GitHub repo that you're going to try out if you want to take a look at it. All right. I want to now showcase 2 of the studies that I have done with our team in Cambridge, UK at Microsoft Research on an Xbox game called Bleeding Edge on human-like navigation in Xbox games by AI agents. We have 2 studies published. You can see here it was in ICML and in the Chi. But the question we were asking is, what makes navigation human-like, and how can we evaluate it in artificial agents? Since more than 3 billion humans play video games, which obviously this number has increased during the pandemic, it seems like navigation in video games is a not biologically, but ecologically valid approach to studying human-like navigation. We chose Bleeding Edge, which was developed by Ninja Theory and bought by Xbox and Microsoft in 2019, because it's a very ecologically valid combat simulation game. It's 8x8, it's steampunk, and it's funny, and I'll show you a video of it later if there's time. And we simplified it into a one-person navigation in the environment of this task. So the first part of what I want to tell you about navigation Turing task is when human judges judged whether an agent was performing correctly. Here you can see that this is the kind of environment, and the agent basically, or a human, navigates there. And I would like to ask you to take a look at these 2 videos if they're going to play in time. Yes. Look at the video on the left, and I'll then show you the video on the right. Tell me which one you think was played by a human and which one was played by an AI. And this is, average player. It's not a novice. It's not your grandma. It's an average player. So this is on the left. And then I'll show you the video on the right, and you can decide which one of them was played by an average player human and which one of them was played by an AI. right, so show of hands, who thinks that the one on the left was played by an average human player? Many people. Who thinks the one on the right was played by an average human player? Fewer people. Obviously, you know, the wisdom of the crowds. The left one was played by a human. I'll show you one more, just for fun. So look at the video on the left and then the video on the right, and tell me which one you think was played by an average human player and which one by AI. All right. Now you're seeing the video on the right, and please let me know which one you think was played by AI and which one was played by an average human player. All right, so who thinks it was the left one was human? Wow. Who thinks the right one was human? None of them were human. Here you saw two different agents play, and this is how we ran the experiment to see which of the agents are more human-like than other agents. So here, human judges would sit in front of two videos, and sometimes they would see a human and an AI. Sometimes, unbeknownst to them, they would see two agents. The agents that we chose were from a paper from that same year in 2020, which was called Deep Reinforcement Learning for Navigation in AAA Video Games. And they were considered state-of-the-art agents. One was a symbolic agent and the other hybrid. The symbolic agent had a very simple architecture. I recommend you take a look at our paper or the Alonso paper that proposed it. And the hybrid agent had both symbolic as well as diminished 3D vision. If you looked at the just benchmark passing of those agents, as you can see in these plots, they were performing equally well on both mean episode reward as well as time to goal. And this is how the participants responded. So just like you guys did, just choosing which of them and then saying how certain they were and writing what were the features that made them believe what they suggested. In the first studies, and we replicated this with much higher ends, we had 6 trials for human versus hybrid agent and 4 trials for the 2 agents versus each other. In the second study, we had 6 trials for human versus symbolic agent and 4 trials for the 2 agents versus each other. And these are different populations. As you can see here, in the 4 questions, for every one of those 30 participants, you can see how often they said the symbolic was more human-like and how often they said the hybrid was human-like. As you can see very clearly, hybrid is the winner. And we thought, okay, they could be primed by the fact that they're seeing the hybrid a lot. So in this other one, we had human and symbolic compared to each other. And that turned out to be that still hybrid was the winner. This is the judgments compared to ground truth of hybrid versus symbolic, how human-like they were. And as you can see, none of them passes the navigation Turing test. So state-of-the-art 2020 agents that on benchmarks perform perfectly on navigation tasks do not pass at all, anywhere near passing the human-like navigation Turing test. And then we replicated this with mTurk participants. As you can see, the variance is higher. And then we did something else, as you can see here. We also did a reward shaping. We said, okay, we're gonna give complete rewards for don't go into walls, don't bash your head against this thing, don't throw yourself off. Like, give them complete reward shaping. And you can see that although the average seems like it passes, if you actually look at the variance, this is not passing the Turing test either. So that was very interesting. We also analyzed the text that people provided for explaining to us why they thought that something was human-like or not, and then compared them. And it turns out smoothness of the physical movement as opposed to just the zigzags and running into walls, things that just humans wouldn't do, were some of them. And we tried to code that and compare them in Chi, and if you in the Chi paper that came out in 2022. And if you have any suggestions, please talk to us. We are actively still working on this. So a very quick summary, none of the state-of-the-art agents passed the navigation Turing test. Majority of human judges thought hybrid was more human-like than symbolic, in spite of the fact that their performance on benchmarks were the same for any kind of measures that we had compared. So the benchmarks were not enough in order to compare the human likeness. The one question that we are pursuing is, can brain-like architecture improve human behavior, or human-like behavior? Can CogSci inspired higher-level concepts for training the AI agent or for creating an AI agent help there? I'll just very briefly mention that we also tried to train Gale-based 6 different kinds of artificial agents to judge human versus, so the same test, but an AI was the judge, basically. We call it ANTT, which is Artificial Navigation Turing Test. And we tried many different kinds of inputs, the symbolic input, the top-down trajectory of the movement, visual input, the barcode image, which is the average of the different images. And we tried these 6 different kinds of agents. Some of them were symbolic, some visual, some used the top-down view or the barcode. Most of them were equivalent to the typical discriminator architecture in adversarial imitation learning, and some of them were related to adversarial imitation learning from visual observation. Long story short, they all perform kind of decent, other than the sort of top-down CNN approaches, and all of them were sort of trained on other data, as you can see. They were trained on ImageNet, they were not trained on this data. Most of them did kind of decent on human versus agent, but if you notice here, they did not do on something you guys were even better at, which was dissociating which of the 2 agents looked more human-like. It seemed like they were completely failing at that. So it's very interesting. If I had only shown you the result on the left, you would have been like, oh, great, we have solved this. We haven't. We cannot even artificially evaluate what makes it human-like. Even though it can dissociate human versus agent, it can't dissociate human-like behavior on 2 agents versus each other. So in the future, once we get this done, it would be interesting to have an inbuilt kind of artificial judge, the way many of us might have, especially after the pandemic, looking around to see what are the codes of conduct of social behavior. We've forgotten how to be at conferences. Likewise, maybe it would be helpful for some of these AIs to have like an artificial judge inside of them that kind of evaluates their human likeness of their behavior in games or environments where they interact with humans and updates itself. One last thing that I would say, and here's where I'm going to show you a little bit of what the actual combat looks like in Bleeding Edge, which is the game. These kinds of videos get hundreds of thousands of views on YouTube. People really enjoy watching it too, which I personally find it very messy because I'm from the Atari generation. It turns out that it could be that maybe task set-based and affordance-based concepts could allow us to analyze these sorts of very complex multiplayer games in a more reasonable way. This is what we pursued with my, This is what we pursued with 2 of my talented grad student interns, Guy Davidson and Kimia Keterpal. And what we thought was, if our goal is to have an interpretable approach to analyzing tens of thousands of complex and multiplayer Xbox games, maybe we can use task sets and affordances. Task sets, as you would find in Sakai 2008 review, or Sakai and Passingham, in another paper, that talk about task sets and the prefrontal cortex, are more generalized notions of tasks that are generalizable across environments. They care about what feature in the environment do I need to select, let's say the color, what operation do I need to do, let's say judge whether it's red, and what actions do I need to take in order to report to the environment my response to that task. They are both generalizable and they are compositional. And Anne Collins's lab actually does a lot of fun work on options, and she's done some work also on task sets, and I hope that we can have a conversation about these more higher level notions and how to bring it into RL. And affordance is when the conditions for doing a task set are met, and it's up to you or the agent whether you would want to do this or not. So as you can imagine, in the game, multiple tasks are afforded simultaneously. What we did was we computed these affordances in analyzing tens of thousands of game data for instance, one character. In that case, it was Ninja. And then we looked at the probability of people choosing one task set versus another from these simultaneously afforded affordances or task sets. Then we did a U-map, and then we said, all right, let's color this U-map by either reward or by the ratio of the task sets that related to fighting versus running away. Beautifully, what it turns out is that reward is not enough to make any clusters in the task set and explain variance in human behavior in playing the games. However, if you look at this broad concept of are you most likely to run away, and when things are afforded simultaneously, do you fight or do you run? Which, as you all know, is very ecologically valid in psychology for both animals and humans. And it turns out, as you can see here, that there is a very nice separation of those things. So this is a nice way of analyzing strategy and variance in human play data in hundreds of thousands of games, which allows online evaluation, allows us to understand and interpret the analysis we're doing of large-scale data with the simple use of very old cogSci concepts such as affordances and task sets. And I think is one of the showcases of why our field is extremely important to inform AI, and so it can help that engineering part if used right. So this is basically using something that's behaviorally plausible for humans on that axis that I showed you, and seeing how we can adopt it to do things that are plausible for the engineering purposes. Something that we hope to do in the future is to find geometry of these manifolds of task set related patterns in order to automatically evaluate the artificial agents and which of them would be human-like. So if remember that the regular approaches did not do well on seeing which of two agents were human-like. So the goal is to use these sorts of analysis and the geometry of task set analysis on an agent's performance on the data, on the game, in order to automatically detect whether this is human-like geometry or not. And that would mean that we don't have to take hundreds of subjects doing a Turing test every time we want to see if a new agent is behaving in a human-like manner. So human navigation Turing tests show that no state-of-art agent passes Turing tests, and we would like to see whether brain-inspired and abstraction of the approaches using cognitive science concepts can generate more human-likeness. We showed that the plausible models failed at rank agents in terms of human likeness, in spite of the fact that some of them did north of 80% in terms of discriminating humans versus agents. And when we analyzed the gameplay data of humans using task set, affordance, and PFC-inspired concepts, we found that we could cluster fight or flight behavior in very large scale, tens of thousands of games. And in the future, we would love to evaluate these agents using geometry of task set space and design RL and deep learning agents that use task sets as a concept instead of being chained to the notion of policies and options, which are environment specific and not as generalizable. So let's go back to what I showed you earlier. I hope I have convinced you somewhat or provided some evidence to support my claim that passing task benchmarks is not enough to have human-like behavior. That behaving like humans in some task doesn't mean that you can actually behave on another task. For instance, for an AI agent, consider the fact that it could tell AI versus human behavior, but the same thing on two agents it couldn't. And that having human brain-like mechanism, it doesn't necessarily lead to, and I think this was from the examples I give from CNN's, kind of jumped over it. So generalization beyond samples, getting human-like behavior might require an approach that is truly looking at all of the axes that I had proposed earlier of human-like behavior, neural plausibility, and the benchmark engineering approaches. And to which extent you might need to borrow or go through each of these in order to create a state space of success for your own directions might benefit from having a standard in the field, some library like what Arthur and I will talk to you about at the tutorials. Some approach that you can have all the tasks in one format and you can automatically run a number of different models on them from the tasks that are important from the field. And so I want to invite everyone, if you think your task should be there, please add it. That's our goal. One of our goals here is to get feedback from you. How easy is it to use? And to also have your tasks added to certain kinds of environments. And if you have suggestions about the structure or how we can improve it, please let us know. With that, I'm going to jump to the next part, and I'm going to run over this a little quickly. These are concepts that we will touch on in a hands-on way during the tutorials. So if it's not super clear right now, and I hope that it is, do come talk to us, and do come to the tutorial and ask the questions. The approach that I take for comparing artificial and biological agents, in this case humans, sometimes rodent data if I get my hands on, thanks to my colleagues, is to first select a series of models, and I haven't put that here. I think I should put that at the 0 step, which is just select what are the plausible models you even want to try, what are your hypothesis space. And then compare behavior on the same task. This is very important, and this is a flaw in some of the studies that I think we need to look critically at, where they are not actually comparing models on the same task. They are changing the task when they're comparing different measures, and that's a dangerous pitfall because it could seem like a particular approach works, but it might not really work. And once you have accuracies, errors, and reaction times, then you can have some of those agents or models performing better than others that then you can take them to test them in terms of their representations. Why is this important? Because for me, there is a primacy of behavior. I know for some people there might be a primacy of neurally plausible architectures, and that's totally fine. So I'm not saying you should always start with behavior. That's my personal preference. You could start from neurally plausible and then move to behavior if that's your preference. Once I have the models that I know that their behavior is neurally plausible, then I can go back here and test whether with electrophysiology or fMRI, what are the representations that underlie that behavior, and can we compare that to the internal representations used by the agent in order to show that behavior? The kinds of examples that I'm particularly I've been fortunate to work in relate to spatial navigation as well as non-spatial hierarchical tasks. And hopefully we'll get to talk about some of them now, but as you can tell from the title of NeuroNav, spatial and non-spatial navigation of multi-step environments is something that's of interest in the particular direction. You all know that behaviorism was toppled by Tolman's revolutionary experiments showing there is latent learning in rodents, showing that rodents were not just input-output models with no internal life. They actually learn things about the environment without them being hungry in cages and given reward only, meaning they could learn the structure of the environment without rewards. Later, 30 years after Tolman's beautiful review in 1948, which reviewed 20 years of research from his own lab and others, O'Keefe and Nadell had this beautiful book on cognitive maps, and 30 years after that, grid fields were discovered. The combination of them showed that there could be a medial temporal lobe underlying plausible neural grounding of what Tolman and others had proposed over 60 to 80 years ago, before these things were produced. And as you can see, this is also behavior first, and then neurons come in. Now, what they didn't talk about was, what do these cognitive maps actually look like? Are we storing one-step things in our maps, and then at the moment of decision, we just, us and the rodents stand there and one step at a time unroll everything and compute everything? While this approach is very flexible, and this is the approach in model-based reinforcement learning, it is extremely inefficient, especially if a lion is coming to eat you or if a bus is going to hit you. You don't want to stand there and compute things until you get hit by a bus. You definitely want to be a little faster in reacting. There have been some approaches proposed of how this will kind of work out. One approach that I am going to talk to you a little bit about is the multi-step representations or relationships between states at different scales that can be captured in the successor representation, and variations of it that I will talk to you about. Why am I talking about reinforcement learning? And I cannot highlight this enough. First of all, some people believe that reinforcement learning is completely behaviorist, as in you need reinforcement or reward in order to learn anything, or external rewards. The truth is, that's not the case. While you're totally right that much of reinforcement learning needs rewards, external rewards, in order to learn, there are many different expansions and approaches to reinforcement learning that are cognitive map-like, that are learning things about the structure of the environment in the absence of any rewards. So with that, the classic RL problem is one in which, given a task or goal in the environment, the agent learns a sequence of actions, and actions could be up, right, left, in this thing that's called a grid world in reinforcement learning, which is a simplification of the environment. Usually it looks like a maze from above. Note that while we are showing the maze from above, the agent is not experiencing the maze from above. The agent is going one step at a time, and at any given moment, it only sees, as in perceives, one state that it's in. Anything it knows about the world is stored somewhere. It could know only the value of actions in a given state, or it could know the map of the environment, or it could know from here I can approximately in multiple steps go here or there. Another thing about it is that there are options that are something that is the focus of Ann Collins's lab as well, which are these notions of abstract. Oh, first I have to say policies are sequences of action. So here you can see this green is one policy. An optimal policy is the policy that in a kind of fastest way maximizes your reward or value, or your discounted reward or value. And options are an abstraction of policies. For instance, you can say, oh, I just want to go from this up left corner to the up right corner. And there could be many different policies that can go from there. So that family of policies, the abstraction of that would be an option. And then there's eigenoptions, where it creates an eigenspace, where these options can be kind of decomposed into components you can linearly combine in order to create behavior in a kind of a more complex environment. An open challenge for the option-based and eigenoption-based approaches is, while it's very easy to find many of them in an environment such as Montezuma's Revenge, as you have seen maybe in the beautiful work of Marlos Machado, unfortunately, it's extremely difficult for in order for the agent to automatically detect which of these options or eigenoptions are optimal or actually relevant to the task at hand. For instance, in the Montezuma's Revenge case. So this is an open challenge for the options approach. All right. The approach, which is reinforcement learning, takes actions, learns representation, some of them, not all of them. There's behaviorist RL as well, and plans to achieve goals. It's neurally plausible, as we will hopefully see in a very short time that I have left. It enables abstraction, hierarchy, generalization, and transfer in different ways. And it can capture very kind of simple ways. My first conference in person in the pandemic was going to Lisbon. So for instance, I could think about just fly to Lisbon, or I could be like, oh, what was it like to be in airports? And just remember what are the steps to go there, and then think about more detailed steps of it. I can go at many different scales of details about how I can plan my flight there. Obviously, if I get stuck with the one step, I would have still been in my apartment planning my Lisbon trip and not made it, even like though it was in November 2021, sorry. Now, another thing that is important is what happens if the coffee cart moves, or my my gate moves, or the transition structures change. For instance, the path that is going to my gate, there is some construction and I have to take another staircase. These are things we immediately adapt at. The first one, when the rewards move, is reward revaluation or reward transfer if you're a computer scientist. The other one is transition revaluation, when, for instance, the steps change, so the transition structures of the environment change, or transition transfer. Model-free reinforcement learning, which I have shown here, and you will see this again in the tutorial, is one where it only caches value of actions in a given state. It does not store anything about the structure of the environment. And it cannot revaluate if things change midway. It needs to go back, experience everything, and update its state action values. And so it has a challenge in these sorts of revaluation or transfer tasks. It's very simply, it stores a table, a lookup table of values of states and actions, and updates them by having a learning rate, which is between 0 and 1, and a prediction error. And the prediction error says simply, this is the reward in the state I have, this is the discounted value of the next state, and then this is what I expected to get in this state. If prediction error is 0, it means I have perfectly learned what is the reward here, what is the discounted value of the next state, and there's no surprises. But if I haven't learned it enough, because human learning rates are somewhere between 0.2 to 0.5, 0.6, and so because it takes a couple of rounds for me to not be at all surprised about a particular value, then I will update it with this kind of surprise, with sign surprise. If you all had a cent when you saw this canonical 1996 paper, we would all be a little richer right now. So I'm just going to put it here for legacy purposes. This was one of the first cases in the 90s already where we saw that there is a neurally plausible correspondence. That story has been changed, a story that prediction error captures dopamine in the striatum, for instance. That story has changed a little bit. It's been more complex now, and you can also see distributional prediction errors, beautiful work that has been done by DeepMind, also represented in the NeuroNav library. If you wanted to test it out, ask us about it also in the aftermath. which is the tutorial. All right, so model-based RL, which just to show you what the cognitive map looks like for a model-based RL, for an environment where you have two different trajectories, one of them leads to reward, stores separately a one-step transition map of the environment, which says, oh, from 1 I can go to 3, but it doesn't tell you that from 3 you can get to 5 or 6. You need to go to 3 and see where 3 goes, and like this, do iteration. This is why you need an iterative approach, or what they call unrolling of your model, in order to figure out what are the trajectories in a model-based case. It separately stores rewards. So at the moment of decision, you need to compute optimal value, which is the V star, by taking actions A that maximize the reward and sort of the expected discounted value of the future states you can get into. This is basically the value-based iteration that you might have heard of, and we are going to discuss it in a hands-on tutorial during the tutorials as well. And as you can see, it has a lot of iterations. You have to sum a lot of steps that you're taking separately, so it takes a lot of time. Another approach I mentioned is a successor representation. Note here, unlike model-free RL, it does not just store a lookup table of values for states and actions. It actually separately states something that is cognitive map-like and rewards. What does that mean? It can learn that successor representation or the map of the environment without rewards. With a simple, various kinds of learning, and I'll show you one of the approaches, and you can take a look at it in the tutorials as well. So the successor representation here is shown as M, thank you, with a given policy and gamma, separately stored, and then the rewards of every state and action. And at the moment of decision, you do this very cheap computation, which is the linear combination of your representations and your rewards, which you have learned separately. In spite of the fact that they influence each other somehow, they are still separate. And like that, your value combination becomes easier. Magical properties of the successor representation, which is not so magic and more scientific, is that the rows of the successor representation tell you what follows a state. For instance, in row 2, I can already see that 2 leads to 4 and 6. The columns of the successor representation show where you came from, show what are the places that you could come to a particular location. So it's showing you the predecessors or the past if it's a temporal sequence. For instance, when you get the column of 5, you can see that 1 and 3 can lead to 5 here already. You don't need to do any kind of computations. Interestingly, my very good friend and colleague, Kim Stackenfeld, showed that the columns of the successor representation capture hippocampal place fields. And in fact, the successor representation's eigenvectors, the eigendecomposition of it, gives you grid fields, which is fantastic, as you can recall. This was some of the approaches to cognitive maps. And using a very simple temporal difference learning approach with no rewards whatsoever here, and we will discuss it a little bit more in the tutorial, you can actually learn that map of the multi-step associative map of the environment with no rewards involved. So as you can see, with very simple changes in an equation, we have immediately gone into Tolman's revolution, and we are no longer in the behaviorist philosophy. Sometimes very simple math actually is correspondent to very different ideologies or theories in psychology, which I think is a beautiful property of this approach. And the successor prediction error, as you can note, there is no rewards here. It says every time I go to S prime, I'm going to visit it. I'm going to say 1, add 1 count, so it's a count-based learning. And then I'm just going to inherit the discounted successors, all of the future of the next state that I've ended up in, and then see if my successor representation had it already. That's the prediction error. The beauty of it, the reason it's multi-step, is that every time I go from one state to another state, I am inheriting all the future of that state, which is a very interesting, I think, concept to think about. And like I said, there's beautiful work from my colleagues and ourselves, if I may say so, on showing that this approach is not only good for capturing behavior, but also for capturing the neural components of successor representations. And if you put it side by side, you can see 2 potential hypotheses about what a cognitive map might look like when we look at neural similarities of different states in the brain, for instance. So already we have a hypothesis for that. The thing that I suggested, which was a kind of missed opportunity, I called it SR-Dyna, then I should have called it Dinosaur, is one where you update your successor representation using a dyno approach, which is basically replay. In this way, you have an even more flexible approach that can update your successor representation multi-step dependencies so you don't grandfather an outdated relationship between some states. And I'll show you what that means behaviorally very quickly. So the task looks something like this. You just go through different states, in which case there are rooms. This is a task that is a modification of my 2017 task that I made for patients. And then you go through state 2. You're navigating on that MDP that I showed you, which is short for Markov decision process. You go to the end, you click something, and you see how much reward there is. And then this could go either, so there's one corridor that was the one that you saw maybe, and then there's another corridor that goes in a different direction. We made different scenes and different music just to make sure people don't confuse in which corridor they are. Now, then afterwards, you're asked, which of the rooms do you think would give you a bigger reward? For instance, if you got 10 at the end of the corridors in one case, and then starting from state 2, you got $1, you should prefer 1. We designed 2 experiments behaviorally first to test whether this is more, which one of these models that I mentioned, model-free, model-based, SR, and dinosaur, produce human-like behavior. The first approach was you learned all of that. I asked you, do you prefer 1 or 2? And you said 1, and I was like, good, you got it. And then in the second phase, I'm not showing you 1 or 2. And, oh, I'm going to need a little more than that, but thank you. 3 to 5 and 4 to 6. As you can see, nothing in the structures have changed, but the rewards have changed. Just to see if you're awake. When I put you back in 1 versus 2, in this case, would you prefer 1 or 2 in phase 3? 2, yes, thank you, the one person in the back. And then I'm going to ask you also, what do you think, do you think model-based can solve it? Raise of hands. A couple of shy, correct hands. Yes, it can. Do you think successor representation can solve it? Raise of hands. Yes, it can. Do you think model-free can solve this? Raise of hands. No, model-free can't solve it because we went back here and it doesn't have, it didn't go back to 1 to update the table of values for 1, so it doesn't. You're totally correct. Yeah, so both of them can solve it because the only thing that was changed was this reward and nothing in the maps were changed either. All right, the next one. Something that happens in New York City is A and F train run on each other, which is extremely confusing. 2 and 1 run each other. You just always have to be careful where you're going. So in this case, that would be 3 goes to 6 now and 4 goes to 5 in the second phase, but the values or the rewards are not changed. And then I throw you back in state 1 or 2 and I say, which one do you prefer? Show of hands, who thinks model-based can solve this? You are correct, model-based can solve this. Who thinks successor representation without replay, so not dinosaur but SR, can solve this? It cannot. Who thinks dinosaur can solve this? Yes, it can. Thank you for people in the back participating. So it's true. The successor representation on its own can't solve it because it's grandfathering a multi-step relationship between 1 and 5. It hasn't gone back to 1 to update it. However, if you're updating it via replay and virtually navigating them, you can kind of see that it works. So this is the hypothesis space. Model-based would do equally well on both. SR would do one, not the other, and dinosaur is going to be asymmetrical. Long story short, this is human behavior. As you can see, control condition, nothing changes, so it's not about people forgetting what they were doing. Transition, worse, and also it's not a speed accuracy trade-off because transition is actually taking more time, and in fact, how much time you took on transition evaluation corresponds to how well you did it, which means the human behavior is much more consistent with the prediction of dinosaur. We also replicated this. I have some things here about the distinction between different, yeah, I have to wrap it up, so I'm just gonna see. Please also go take a look at various kinds of prioritized replay that we published with Samuel Barnett. We call it parser priority adjusted replay for successor representations and compare representations that learn depending on what kind of replay prioritization you had. And just thank again my grad students and postdocs. All right, thank you.
Thank you so much, Ida. We have time for, I think, maybe 1 or 2 quick questions, and then maybe in the meantime we can have Constantin set up as well.
Hey, very nice, fascinating ideas. I want to catch you afterwards and have lots of discussion, but I want to ask you and come back to what you started with this idea of using the Turing test as a way of testing things. Because humans are notoriously bad at the Turing test. And I want to actually ask you, when you think about the Turing test for humans against humans, which is, of course, where it originally starts, right? It was a Victorian game. Yeah. What do you think about in terms of things like neurodiversity and in terms of issues of, say, skill sets, yeah. Right? Because I suspect that if you have them looking at humans versus humans, they will very happily call some of the humans not human.
Very grateful you asked that question. That is exactly the reason we did the task set type analysis that you saw, to look at the diversity and variance in human behavior, for instance, whether it's in fight or flight or something else, so that when we are looking at human-like behavior, we can use automatically the geometry in that manifold of task set probabilities and tendencies of actual human play data and assess the human likeness of our models like that. Right. And another reason that I showed you the huge variance in the navigation Turing test was exactly to show you this is a very difficult approach. However, we had those cases where humans were at 80% saying that this is not human. And I think in those cases, it's reasonable to say that agent didn't pass the Turing test.
All right, maybe last question over here.
Hi.
Hi. So thank you so much. I also want to go back to the beginning of your presentation and also link it back to some of the conversations we had the first day. So you were talking about human-like AI, and I think most of the people in this crowd are interested in that because by engineering more human-like AI, maybe we can better understand humans. But do you think there's also something to be gained on the purely AI side? Because you mentioned that hitting a benchmark does not necessarily mean human-like AI, but the reverse is also not true. So more human-like doesn't
Absolutely.
mean hitting better benchmarks. So where do you stand there?
Thank you so much for asking that. Your beautiful question is exactly the reason I made the rubric to have 3 different kind of components. One of them is engineering and benchmarks, and the other one is human-like behavior, and the other one is neural plausibility. None of them guarantees the other side. And you are absolutely right, and that is exactly the reason I made that rubric. Any approach that's human-like behavior, it could be like on a 0 or a 1 or a 2 on the approach of engineering, but it doesn't necessarily mean it's gonna solve that. And it absolutely means that there is no need for somebody who's actually interested only in the engineering and benchmark to worry about human-like or neural plausibility. So it is only for those that actually want something that's between them that they can occupy that part of that state space of the rubric. And you're absolutely perfectly right that none of them necessarily guarantees that progress on one field translates to another, although there could be some hypothesis about the correlations, and we could make educated guesses or hypotheses. And there could be sometimes some lucky happenstance there. But you're totally right that that is exactly the directions of the rubric, and I think that you could do one without doing any progress on the other.
Thank you.
Thank you.
Please join me in thanking Ida again for a fantastic talk. I'm going to introduce you. Okay, so our next speaker is Constantin Rothkopf. He is a professor at the Institute of Psychology and the founding director of the Center for Cognitive Science at the Technical University at Darmstadt. He is also the founding member of the Hessian Center for Artificial Intelligence. And his research interests really center on the distinction between looking and seeing, and how this distinction relates to vision during goal-directed actions in the real world. And I think why we're particularly excited about his research and this keynote and tutorial is that it really moves beyond, his work in general, really moves beyond studies of passive perception and tries to relate perception to cognition, planning, and action, and study the intersection of the interplay of all these abilities in humans. And so to tackle these problems, his lab takes an interdisciplinary approach that looks at human behavioral measures, as well as computational models with methods from statistical methods and machine learning methods. So please join me in welcoming Constantin.
All right, great. Thank you for the introduction, and thanks for the organizers for inviting Dominic and me to this conference, which I think really fills a void in the landscape of conferences, which is really important. All right. Better now? You can hear me better now? Yeah. Okay, great. All right, so we have tried to make both the keynote and the tutorial a bit of both, so that you hopefully can get as much out of this as possible, of this format, so that you really consider also using continuous psychophysics in your work, and possibly the analysis method that we have recently introduced. All right, so just as a roadmap, I'll first talk about 3 bit more conceptual points, and after introducing those conceptual points, I'll give you some examples how we have used those in the research in our lab. And from that, then I think you'll have a pretty good idea why we are approaching continuous psychophysics the way we did, and Dominic will give you all the details. So in a way, I'll be giving you the abstract and the introduction, and Dominic is giving you the important sections of the paper, like the methods and some of the results. All right, so normative versus descriptive models. What's up with that? Well, so the central motivation for using probabilistic normative models is the fact that the world is ambiguous, uncertain, and noisy. And so, right, the way of how to think about this is usually there are infinitely many objects that can give rise to the same sensory inputs, and one and the same object can give rise to many different sensory inputs. If the sensory input is particularly uncertain, then the effects of the prior become more pronounced. You can also look at stimuli that change over time, so then you can have sensory measurements that are combined sequentially to reduce the uncertainty about what's out there in the world, like in these evidence accumulation experiments. And in motor control, it's very clear that you think about motor actions being noisy in the sense that there is outcome variability, but that there are also consequences of actions that depend on the intrinsic world. And finally, of course, there are physical properties of objects, also when you have to do reasoning about that and reasoning about their dynamics, where you have really an intricate relationship between all of these different, this multitude of uncertainties. All right, and so these computational models that try to make these uncertainty explicit, they allow you to formulate these normative models. That is, they answer the question, well, given the involved uncertainties, given my model of the uncertainties, can I specify the goal of the computations? Well, then I can derive from that an answer to the question, well, how should the system act? How should I actually act? I think at this conference I've seen it now at least 4 times as one of the prime examples. And I also think that's one of the success story in computational cognitive neuroscience, that there is a general theory of how to do well sequentially. And there is, from that theory, you can derive lots of different algorithms. And there's one family of algorithms, temporal difference error algorithms, that you can also implement them using neural networks, where there is a particular variable, this temporal difference error. And that's a really interesting variable because it's not just out there, right? It's the reward, but there's cognition too. There's this internal prediction that you derive. So it's not all image computable. It's not just the sensory stuff out there. It's cognition. It's stuff that is internal. All right, and it has been related, as has been just said again, to midbrain dopaminergic neurons. And yes, of course, the picture is oversimplified, especially due to work that we have the last years. But I think it's a great example where these computational models, right, where the way of describing in computational terms what the goal of the computation is, has really played out in helping us to understand what the system is doing. All right, so in the spirit of a tutorial, more tutorial than a keynote, let's look at the components of some of these models. And I know for some of you this is, you're falling asleep because you're teaching this, but maybe for some others, you haven't seen this in the context and how this leads up to our modeling of continuous psychophysics. So the idea of the generative model here is, Well, there is some unobserved state of the world, right? The distance of an object, the shape of an object, the identity of an object, let's say the speed of an object in the world, and you don't have direct access to this quantity. So that's the state of the world, the latent state of the world, and for the purpose of this tutorial, we'll use the notation that is common in optimal control, that's what we call X. And then we have a sensory measurement, and the generative model tells you how this comes about probabilistically from the state of the latent state of the world. Okay, so here we don't have any actions, right? We don't have decisions, we don't have actions, we don't have rewards, anything like this. So if you actually introduce this, so now you have controls, the use, you have the rewards, and you have now a temporal evolution, then you get to this particular model here, which is the so-called partially observable Markov decision process. And what you can see is, right, there is this slice here is reminiscent of this model of perception, but now you have these slices over time, and you have these actions, and you also have the rewards. Now, you can come up with, right, models for a large variety of tasks. There's a nice paper by Peter Dayan and Nathaniel Daw, where they try to relate many of the common experiments in neuroscience to these types of models. You could also look at Russell and Novick AI, the chapters on agents, where you can really now relate many of these experiments that have been done in the lab to their model. And what's a little bit unfortunate is that these right, circles and arrows hide the complexities of these models, the relationship, the really intricate relationship between variables that come about. Let me give you maybe one example here. So if you have something like a Kalman filter, right, you're doing only inference. It's not clear what you should actually act upon or what the costs and benefits even are. In MDPs, many of you may be familiar with the exploration-exploitation dilemma, right, where it's about, well, how should I actually pick an action to learn more about the environment, and how should I use what I already know? And in a way, you can have POMDPs make this problem completely disappear. There is no exploration-exploitation dilemma, because relative to the beliefs, you can show that there is an optimal way of actually balancing exploration-exploitation. And so, unfortunately, this gets lost in just, random variables and the graph connecting them. But these models are incredibly intricate and have many properties. So many of the properties you know from active inference in POMDP, they just, boom, they just appear very naturally. Curiosity is in there. All right, I could talk another tutorial on that, but now I have to focus. All right, now you have these generative models, so what do you do with them, right? How do you go now about thinking, well, what do humans do? Well, the first thing to try, and the first thing that is of course very popular, is to say, well, I'll take now this model and I'll, how it's often said, I invert it. And so this is what you often find referred in many books and many papers that are very popular, that have become very classic. Over the years, you apply, let's say here, Bayes' rule, where you invert. Now you want, given your sensory measurement, now you have an observation, a sensory measurement, and now you want to infer, well, what is the state of the world? So what is the actual state out there in the world? What is the probability distribution over there? What's my posterior? Okay, so that's what these are good for. And so we'll try now to use that to address the question that I think is also very central to this conference, right? We often hear, oh, the stimuli are more complex or more rich, but what makes a task natural? So since my PhD, I've been working and really trying to get a hold on this natural sequential behavior of human, like making a peanut butter and jelly sandwich. And so here you can see a rendition of the eye movements of a subject coming to lab and actually making a sandwich, right? And so here you have something that is really sequential perception and action manipulation of the environment. And if you look at the behavioral literature, you find notions for this that people have somehow most probably learned when to carry out eye movements, so to coordinate temporal eye movements, and there's this notion that people plan gauge sequences. And so the connection to what I showed you previously is, well, okay, but how do we show this computationally, right? All right, and so the idea is, okay, well, let's take this seriously, that we have to think about what the probabilistic models are that describe these situations, and then we can go through the list of things that specify what is the state variable that describes the state of the world. What are the observations? What are the actions? And this is a partial list, but it's a list with many important properties. And the nice thing about this is you can directly translate these in probabilistic models. Right? So these are properties of tasks, and you can use them to specify, hey, what type of a task do I have at hand? And so classical psychophysics 2AFC tasks, well, they don't have lots of these probabilistic, well, their structure is very simple in terms of their probabilistic structure. And if you look at some of these tasks like games of perfect information, where there has been extreme, fantastic developments over the last years, by comparison, the tasks themselves, they don't have all of these additional uncertainties that for us as humans in our daily lives, making a sandwich, are pervasive and that we are handling all the time. Right? Okay. So now inverting models. So what's that? What's that about? Well, the way I showed you the ideal observer, right? What you do is you think, for example, I think Dominic will show you the details, but in psychophysics, for the ideal observer, you always assume the subject has the correct model of what's going on in the experiment. Okay, so for the 3 trained subjects who for 30 years have been doing 2AFC, that may be a good assumption. But for naive subjects, that might not be such a good assumption. And in more natural tasks, how do we know what the uncertainties are of a cup standing in front of you on a table? That's difficult. And of course, the trial structure, well, what trial structure, right? You came to this room, you sat down, difficult. What are the costs? Well, there are maybe external costs and benefits, but what are the internal ones, right? Like you're getting tired or you're bored. All right, and so the idea here is that we have really worked on this for a long time to try to say, hey, how can we try to invert these models so that we don't say, hey, here is the generative model and here is the ideal observer or here is the normative model, but to try to ask, well, what would be behavior optimal for? So let's try to find out what are the beliefs that people have. Can we find out what the internal rewards were? And maybe even their models, their internal models. And of course, not wanting to look too preposterous with this list of references on inverse reinforcement learning and stuff, we're not the only ones to think about that. There are plenty of other people who have also thought about using these inverse model in very different contexts, sometimes in the context of theory of mind, sometimes just in single trial-based experiments, sometimes also in sequential ones. There's work in the machine learning community of inverse POMDPs, and there are also there's more recent work on applying it in the context of neuroscience. And so the point here is, well, what the subject has to do is very different from what we as researchers have to do. Well, we know what we put in the experiment, but we don't know what the beliefs of the subjects are. We don't know what the rewards, the internal rewards of the subjects are. And the question is, are we able to reconstruct that? All right, and I wouldn't be here if we hadn't tried several things to get at that, and that's what I'll try to show you next. All right, so let's motivate this by a picture like this, and I know I'm a culprit like many of my colleagues. We show these very complex images, and then we show little tiny disks and gabors, but I showed you something about the probabilistic structure, and so I hope I can convince you that some of the tasks we use here, they are so rich in the probabilistic structure that they're actually meaningful. All right, so let's say you have to detect events, what's going on in your environment. You don't want to be run over by a car, you don't want to collide with pedestrians, so what you have to do is you have to have some idea about the event statistic structure of your environment. And what we'll now do is we'll have an experiment in which subjects have to detect a little transient event, which is this little tiny white dot in a black disk disappearing. There are two disks, one left, one right. There's only one event per trial. It can be with equal probability on the left side or on the right side, and it's immersed in a sequence of trials, 20 trials, in which the duration of an event is the same on the left and the right side. So in this particular trial depicted here, we have always short events on the right side and long events on the left side. And these 20 trials are immersed in blocks, 30 blocks in total, where at the beginning of the block, subjects don't know what this event structure will be on the two sides. So the logic here is, right, there is uncertainty about what is the mapping, there is uncertainty about what are the durations, and people need to now learn over the trials what these durations are and hopefully adapt their behavior. And again, note, right, I picked this out because it's a notion in the peanut butter and jelly sandwich making literature. Well, people can learn when to look. Okay, let's just look at this behaviorally. Here's data from one single participant, and you can see, yes, right? In the first trial, they looked equally at the two sides. They spent equal time at the two sides. And then they shifted their behavior so that they looked longer at the short event duration sides. And if you think about it for a second, it makes perfect sense, right? Because then you're bound not to miss. All right, so behaviorally this works out. We have 6 combinations of short, medium, and long duration, and we see that there is an effect. Well, we can look at the behavior a little bit more closely in terms of performance, and funny things happen here. So what you can see here is that for the more easy conditions of medium, 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 long, and long, long, people get worse over trials within a block, right? So that's funny. So the good thing, what we can do now with these normative models, because we know the exact probabilistic structure of our task, we can find a normative model that fully captures the probabilities involved in this. And we can compute straightforwardly an ideal observer that tells us, okay, what's the probability of missing an event if I have a certain way of switching? So I switch with a certain rate, I stay a certain duration on left, a certain duration on right. Compute for me what's the probability of missing an event. All right, and so here now comes the usual approach that we pick. So we start with an ideal observer, and the ideal observer tells us, well, switch as fast as you can. So an ideal observer, of course, is not a particularly smart choice for this type of an experiment because there is no notion of actions, right? So what do we have to do? Well, we don't only have the uncertainty about time that is here, so a Weber law on timing. What we have to do is now we have to also have the action variability. That's well known. We can measure that separately. We can also fit it to the data. And so now we have something that we call an ideal actor because, right, there is irreducible action variability. But that's not all. So the next step is to come up with a bounded actor, and we call it bounded really not because there are bounds in that way, but we think about this really in terms of Herb Simon's idea of bounded rationality, that there are internal costs to the agent, that here we used a particularly simple way of parameterizing this with the sigmoid function. Again, we fit this to the data, and already the match is getting much better, and then we have also put in some constraints that are known from literature because it takes a certain time to recognize something when you make a fixation, and then you have to take a decision, and then you have to plan the next saccade. That takes time, and we put that also in the model. It captures the data quite well across subjects, but it's not all, right? And you could say, oh yeah, but you had 3 parameters. Well, we didn't use the learning at all, right? We only looked at the behavior at the beginning and at the end. So how could the learning play out? Well, you can now make a normative model, probabilistic model of learning, right? Sequential updating. It's the same as integrating evidence, but here it's now trial-based. Let's try to see how well does this fare conditioned on the bounded actor. So this is not optimal, it's the optimal learner conditioned on the bounded actor. And we can capture the data pretty well for the learning. Details in the paper to see that all the components are really necessary for this. And finally, we have to do always proper model comparison to see whether the model really captures the data better in a meaningful way. All right, so what have we gained? Well, what I want to convince you of is that these normative models, right, we could also have done what I did during my PhD thesis. I just had reinforcement learning agents try to learn the same task that my participants did. But here with these normative models, you can really quantify in terms of costs, benefits, and beliefs how people did this task. And so we saw that they got worse in the easy conditions, and that's because they traded task performance for doing less eye movements, right? So on average, they were willing to give up 1.55% detection probability in the task for doing one less eye movement. And that's, I think, the power of these methods, that they can really quantify behavior in these types of, in these quantities. All right, so the second thing I alluded to was planning of eye movement. So planning is something very specific, right, computationally. And in visual search, people have had different ideas where you would look. Maybe you look at the maximum of the posterior probability of where a target is. So you look where you currently believe the highest probability is for the target to be. And then people have seen that sometimes you look between two potential targets, and that comes out if you use something, well, that some Jiří Němeček and Bill Geisler called the optimal searcher, where the idea is after the next look, so you look where after having looked there, you have updated your posterior in such a way that you can take the decision best. That's not the optimal that you should do. Let's try to think about the minimal experiment to carry this home. All right, so here's this funny irregular shape. And what we'll have is we'll have a target. And subjects are instructed to find the target. We'll do this in a gaze contingent way, so we will only show a limited area around your fixation point. And then we'll restrict our participants to either be able to do one single eye movement or two eye movements. And so they have to find this target, and now that depends on where they look, what probability they have to detect it. So let's think about this in terms of, again, a generative model of the behavior. So if you do the greedy thing, oh, let me look where after the next look I will be best able at distinguishing it, then you have the prediction that this model will really look at the center where you have the highest coverage, and then you detect or not, and then you go to the next best. But that's not what planning tells you what you should do. Planning tells you you should pick a sequence, if you are allowed to do two eye movement, where the coverage overall is maximally. And that's one of these beautiful cases where there are lots of properties of these models, of these planning under uncertainty models, when you also have perceptual uncertainty. So it's not your common Markov decision process RL, but this is POMDP now. You have these beautiful intricate predictions that you may do an action that trades off gaining information with getting you closer to your target. And so after the first action, you may incur a cost, but over the entire sequence, you may actually do better on average. Okay, now we have two models, and we can generate lots of shapes, and then we can actively search for shapes, experiments that will disambiguate best our two models. And what was really interesting, we weren't necessarily expecting that, was that there are also shapes where the predictions actually match quite well. So where you couldn't, with those experiments, distinguish between the two, right? And we thought, oh, cool, this reconciles possibly some literature. Well, our reviewers thought that was funny, I don't know. Anyway, so what do people do? To make a long story short, if you're interested, the details are in the paper. The behavior of our subjects matches quite well with the ideal planner. So people seem to be able to do planning. There's a little bit of an undershoot. And as usual, as I showed you before, we now augment. We start from the ideal actor, but now we have more components to actually have, well, to make the planning follow some constraints that are also known from the literature, so it becomes suboptimal, if you want to put it that way, because we implement these constraints in the planning, and in the end, as usual, we have to do proper model comparison, and in all cases, the planning model with and without the extension fared better at explaining the data that we had. All right, finally, I made it to continuous psychophysics. So what's continuous psychophysics? So I visited UT Austin, and Larry Cormack said, oh, Constantin, come to my lab. I'll show you something. I think that's something for you. You do this perception action stuff. We came up with this new experimental paradigm where instead of doing 2AFC tasks, we also have these stimuli like blobs immersed in some noise pattern, but instead of people doing hours and hours of 2AFC, well, they sit in front of a monitor and we track their finger. So they really have to try to follow the target, the blob, on the monitor with their finger. Well, we also did it with a mouse, and we have also done some experiments with people tracking it really with the eyes. But here's a data set where people really tracked it with the finger. All right, and so the data is much richer, of course, than false alarms and correct rejections or something. So you have really the track of the target and the track of the finger. And so Kate Bonnen and Larry and colleagues, they looked at the cross-correlogram of that as one way of finding differences between different conditions. And then they also very carefully measured the 2AFC thresholds, and they saw, well, there was a discrepancy between those measures. And so they were wondering where this was coming from. And since then, there have been other authors with other experiments that are really interesting. So there is interest in doing more with this continuous psychophysics because subjects report it to be fun, intuitive, and it's much shorter, right? And if you have ever done a 2AFC, you know hours and hours contrast discrimination in a lab. That's not fun, right? All right, so the task here is track the target with your finger, with a mouse or an eyes. And here's why it's really an interesting task, because from the task structure, it does actually have many of the properties of tasks. So if you want to say it's on a continuum, it's really approaching more naturalistic tasks because the probabilistic structure has many of these uncertainties that make a task naturalistic. So just to flesh this up briefly, I know some of you are experts in this and others haven't potentially seen this. Dominic will be giving you the details of this particular way of modeling in the framework of POMDPs, but now a special type of POMDP that uses certain assumptions, which is the linear quadratic Gaussian case, and he will show you how this exactly plays out in using to model these data. All right, and so what's left is we have to think again, okay, how do we think about this inversion of the model now? Well, we have now to move from the subject gets some sensory input, but we as researchers, we know the exact stimulus we put in. We don't know what the subject internal sensory stimulus was, and we don't know necessarily what the intended action was. All right, we see what they pressed, the button they pressed, but that becomes much more non-trivial if people have, continuous movements of a finger. So there's a distinction here in our model also between the intended action and what we observe as an action that came out of it. And now we have to transfer this to this sequential perception and action. And yeah, so that is not necessarily totally trivial, so we had to work quite a bit to get an analytic solution to this, that we can then also do inference with probabilistic programming. Again, Dominic will tell you more about that. And then we do the same thing over, right? So we have now the tracking data of a subject. We can simulate that also with our models, and we can first think about it really in terms of, well, maybe they're doing just a perceptual task, right? We could think about this in terms of a perceptual task, and then we end up doing essentially a Kalman filter. But where are the actions, right? Well, we have to add them, right? It's, we have to have explicitly actions here, and that also entails then a formulation of what is the task actually. So we have now a cost function that can now describe exactly the tracking, right? People don't want to do optimal inference anything, they want to track with their finger, and that's a difference. We also have now the variability and the actions. All right, so we could stop there, but because we are always thinking about it, really the goal is to get at natural behavior. Well, what do we know about what people's assumptions and internal costs are, right? I mean, the favorite is, of course, for many of us, the favorite is if you're being told, oh, here, do a 2-banded beta Bernoulli independent rewards task, right? But what is it doing? And that's the same for what we do. Oh, just do contrast discrimination. We don't know what's going on, right? And there are all of these sequential effects that suggest, well, maybe we have to include in our models also these cognitive factors. All right, so what is it here? Well, we can start by adding costs, internal costs. It could be effort costs, it could be cognitive costs, movement costs, biomechanical costs. We don't specify this here, but you can now use this, right? Of course, also to get at that. And the final one is by saying, well, maybe subjects had a completely different model about how the objects, the target, actually moved. So the movement of the target is as a random walk, but how do we know that they're really using the same random walk that we put in as researchers? Right? In an ideal observer, you would of course do this, but necessarily it doesn't have to be so. All right. You'll see in the tutorial, inference is possible in this framework. That is, we found a way of finding really an expression for the likelihood. And the really nice thing is that you can now also try to see in a principle-based way whether recovery of the parameters is possible. You can also see how much data you have to collect in comparison to a 2IFC. And the beautiful thing is you need about a maximum of maybe 10 minutes worth of data. So this is really cool also if you are maybe working with children or infants. Needs to be tested, needs to be tried out. If you're interested, we would be excited to help you out and get this working in your lab. All right, so let's revisit the data that Larry and Kate Bonnen collected in their lab. And so here are the 3 subjects. And what you can see here is our reanalysis of the 2IFC task, the Kalman filter, and the subjective model. And there is still quite a bit of discrepancy for the lowest contrast. So there is something there that our model is not capturing yet, which is exciting because now we're thinking about how we could approach this. But of course, this, right, the whole spiel here was this is not only a perceptual task, so it's not only about getting the perceptual thresholds, but it's trying to get also at these other quantities. So what we can extract now for these 3 subjects is the individual motor variability, the internal costs for making the movement, and we can also get at their implicit assumptions about how the target actually moved, right? So what were the internal assumptions about the random walk that was displayed on the monitor? What you can see here is, well, nobody nailed it, right? If you know the abbreviations and you can identify people here, then you can at least say the most experienced psychophysicist was closest, but he was still off, right? All right, And as usual, we do proper model comparison to at least adjudicate between these models that we have here. Of course, there are many other models that we could think of, but at least these quantify now the behavioral costs, the internal subjective utilities people have, their subjective assumptions, beliefs about the stimulus, so to speak, the experiment, and their uncertainties. Okay, last thing maybe to show, well, we also extended this to signal-dependent noise. So if you're interested and maybe come more from the motor control side, so we are looking at optimal control with signal-dependent noise. We have also an inference method where you can recover now the cost functions from those types of experiments, where you again can belief tracking. So you have an experiment and you can now find out what was the uncertainty actually internally of the subject, say of the target position. What was the internal uncertainty of the subject, where their finger was, where the target was, and what was their individually internal cost for making these movements. All right, so in conclusion, probabilistic generative models of task allow deriving these normative models of behavior, and I think this is a way of really getting at, well, what makes a task natural, right? What makes a task naturalistic? And it's the probabilistic structure. Inverting probabilistic normative models reconciles normative and descriptive models, because now you are using these models and are not saying, oh, here, this is my cost function that I think best fits something. No, you are getting a posterior, right? And you can do proper model comparison now. And it tells you, well, what would it have been optimal for, right? And of course, applying it now to continuous psychophysics, if you're interested in getting into these types of experimental paradigm, you can not only recover very, very quickly in a kind of fun experiment these perceptual uncertainties, motor variability, subjective beliefs, also the subjective internal model about the stimulus out there, as well as the subjective costs or utilities. And we're excited about this because we think that it makes it maybe more attractive to use continuous psychophysics paradigms. All right, so I have to thank the people in my lab. So David Hoppe, he was involved in the first two studies that I showed you. And Dominic is here, he'll give you the tutorial. And Matthias Schultheis was involved in the NeurosCience study on the on inverting the model for signal-dependent noise. All right, I have to thank my funding agencies, and if you're interested in these types of things, we have a line of really cool experiments that we are running that are more and more naturalistic. There is even peanut butter and jelly sandwich making involved, so if you're interested in this, just come see me, contact me. I'll be happy to talk about it. All right, thank you.
Thank you, Constantin. We have time for a couple of questions.
Hi, thank you very much for that talk. I enjoyed it a lot. So I was thinking, I was wondering, a lot of what you're doing is in continuous space and stuff. How do you think these methods kind of interface with like discrete problems, like things like chess or mazes, or how you might even integrate them, like kind of mixed hybrid systems type modeling? Is that something you're looking at?
Okay, so I think that the tutorial is for you, because the thing, right? I mean, so
that's why I'm here.
Yeah. So unfortunately, I cannot give you a trivial, straightforward answer. So there's an entire field dealing with when can you, in these types of model, even do inference, and that's totally not trivial. I totally skimmed over that, and I try to defer it by saying, okay, we do model comparison. So the first question is, well, it totally depends on the problem, whether these inferences will succeed or whether you get lots of meta-mares because, right, it's the same for us researchers as it is for perception. You can have many models giving you the same data and many data sets coming from the same model. So it's at all not trivial, but you can see in the tutorial how for different examples you can come up with the respective model and then see whether you can do the inference. I'm sorry, I'd like to say, oh yes, of course we did this all, but yeah, all right.
Thank you.
Thank you for the wonderfully lucid talk. I was going to ask the same question as Mark, but I have a second, which is the ideal planner stuff you presented. So I'm just curious about the bias towards coverage in that framework. I'm not too familiar with it. We've done in our lab a bunch of work looking at how electric fish and visually guided moths and olfactorily guided cockroaches sample, and they do ergodic distributed sampling where they sample proportional to the expected information gain with a cost function on the energy of movement. And so in your planning, ideal planning, or the ideal planning framework you discussed, this bias towards coverage, is that because of lack of consideration of energetics, or where does that come from?
So I presented that particular study as, if we want to say really computationally they do planning, we have to carry that home computationally. What is the most simple experiment to try to show this? And I showed it to two saccades, right? So we have lots of work going on in the lab at the moment, which is getting exactly at this. Well, are they planning the entire day? Of course not. What is their planning horizon? And what we can, well, I shouldn't talk about all of this stuff that is totally ongoing, but people are extremely good, at least in certain circumstances, to quickly adapt their planning horizon, at least when it comes to eye movements. I don't think this is something, right, we have always to overstate in certain types of papers our results, but for eye movements, we see situations where people very, very quickly, and without learning, they quickly change their look-ahead horizon. So I think these types of methods allow you to get at it and to quantify it. You can always do the comparison between individuals because we see lots of individual differences and get at this. But I don't have like the, people always plan this and this, and that's the horizon, and that's these are the costs, right? I mean, we did have in the planning to include three additional factors that made the planning suboptimal, if you want to put it that way, and that matched the data much better.
I see. Okay, excellent, thanks.
No?
All right, last question, but we'll have plenty of time in the break in the tutorials for more discussion.
Hey, yeah, that was so awesome. Thank you so much. But I wanted to follow up on that last thing you said about suboptimalities. And I really want to ask whether or not you think including those effort costs require like debasing us into an implementation level explanation. Because they're in the LQR not because of implementation problems, but to ensure the invertibility of the B matrix. And that might be particularly useful when there's many more degrees of freedom in the action space than there are in the outcome space, like in Bernstein's problems. So do you think we have to resort to it being a suboptimality or subrationality, or do you think those effort costs are there for a good reason?
Okay, so I'll give you an answer that I will have fewer friends if I put this the way I'm thinking about this. So in our hands, when we try to make strong commitments on the algorithmic side, right, we pick a particular algorithm and we say, okay, now we have all of these properties of the algorithm. That sometimes fits the data real well, but in our hands, many of these algorithms are incredibly brittle, and you can change some hyperparameters and they behave very differently. So I'm a bit wary of making commitments at that level. So what I presented, I stayed totally clear of exactly these kinds of things by saying, oh, these are kind of internal costs and internal beliefs. I'm sure that's correct. Now, if you say, well, but here I have this nifty experimental paradigm with which we can dissociate maybe the planning or the uncertainty that people have about which task they're in. And then we go at measuring the costs and we can compare them between conditions. Then my guess is we're getting closer at really pinpointing, oh, maybe this part of the cost connects really to the planning cost. And then you can think maybe, right, of course, getting some physiology and regressing it to it. Because again, right, that's the point about the temporal difference error. This is not image computable because it's internal. Right? Those are your internal assumptions about what's out there. Those are the internal costs and benefits. And the method at least gives you an idea how to measure them, how you say where they are located or whether that's implementational. Let's talk about it and think about it. But yeah.
Thank you.
Okay.
All right, let's thank Constantin again. All right, and so we're going into a break now, and